One of the biggest challenges that students have told me they find in this section is, Mr. Dewick, when do I go gravity is what's pulling me in a circle? When do I go work equals change in potential plus change in kinetic? And when do I go, this is a job for conservation of energy, KE initial plus PE initial equals KE final plus PE final. So I want to talk a little bit about that. Sarah, I'm going to be bad. Do you have your phone? If you do, put it away. Was there a phone on your desk? No? Oh, sorry. I thought I saw you typing. My bad. I completely falsely accused you, and I apologize. I thought you were Ben. Right. Yeah, easy understand. Okay. So, a mass little m, rocket ship, let's say, is moved from the surface of a planet to a distance big R from the center, like this picture. Which of the following is true about the work done? First thing, look at the picture. Are we in a stable orbit or not? The reason I know that, if we were in a stable orbit, the rocket ship would have to be pointed that way so that we were going around in a circle or down below. But I need kinetic energy to go around and around and around in a circle and stay in a stable orbit. So this picture is meant to indicate that we're not in a stable orbit, as opposed to this picture, which is trying to show to you that we are in a stable orbit. Is that okay, Madison? Okay. What does this want me to find? Which of the following is true about the work done? Let's see if we can just write the correct equation ourselves and then find it in A, B, C, D, or E. Oh, this is so easy. I can go work equals gravitational force times distance. Or can I, Keegan? Why can't I do that? So you know what? A is wrong. Right, Jan? You're not that important. Okay? A is wrong. Oh, and I guess instead of distance, I should have used big R, but still wrong. So what definition of work am I going to have to use? What we called, Lena, the work energy theorem. The fact that work equals the change in potential plus the change in kinetic. Although, since we're not in an orbit, I think what we're doing is we're starting and ending at rest. I'm going to ignore that. If we were in an orbit, we would still assume we're starting at rest. Where did we decide we're launching from? Santa's workshop or Superman's Fortress of Solitude, North Pole. So we're starting with a velocity, a speed of 0, but our final orbital speed is v orb, which was gravity is what's pulling me in a circle. You could derive it, but some of you might have memorized it. Okay. Well, boys and girls, what's changing anything? So this is going to be PE final minus PE initial. Oh, that's easy. Don't write this down. Why can't I just go MGH final minus MGH initial? Yeah. And you started to see a little bit the last couple of days why rocket science, among other things, it's just a lot of calculating, and it's not convenient numbers. So which version of a potential energy equation am I going to have to use? Our cosmic one. Read it to me from my formula sheet. Negative, big G, big M. And I think our final is big R. Look at my picture. Yes? Minus negative, big G, big M, little m, all over. And I guess our initial is little r in my picture. You okay with that? What's the correct answer? B, C, D, or E? Sorry? D? It's a plus. Oh, minus minus is a plus. Yeah. Now, is there a big G in everything? Is there a big M in everything? Is there a little m in everything? There is a GCF. Don't write this down, but just, you may see some textbooks write it this way. They factor out the big G, they factor out the big M, they factor out the little m, and then they have negative 1 over big R plus 1 over little r. Although instead of writing negative plus, they'd probably go 1 over little r, take away 1 over big R. I've seen it written that way. I don't know. I've never spotted the huge advantage of that because especially R is on the bottom of two fractions. If you're trying to solve for R, it's fairly yucky. It's a little bit cleaner maybe, but that's what they were trying to get across, I think, when they were having some of this stuff in brackets. So if I had seen that, I would have said, yeah, okay, but I don't see that anywhere. It says explain your answer. I think we derived it. Okay, I'm not going to bother explaining it. What I'd like to talk about is escape velocity. First of all, the name drives me crazy. It should be escape speed because we're going to use conservation of energy, GG. It's a scalar, but in the industry they call it escape velocity, so I'm going to call it escape velocity. What's escape velocity? It asks, how fast do you need to get going on your rocket before you can shut off the engines and coast to the edge of the universe? How fast do you need to get going to escape your planet's gravity well? If I phrase it very carefully in the physics definition, first of all, to escape from a planet's gravity means, in theory, to travel out to infinity. In reality, it means to get far enough away that gravity is so close to zero that we can ignore it, even though it's technically still there. To barely escape means to do it so perfectly. So, again, we need my planet analog. If you could help me again. Here's the Earth. Here's my rocket. What I'd like to do, starting on the Earth, we're going to ignore air resistance because that makes it yucky. I'd like to fire my rocket so that I can shut my engine off and I can coast. As I coast, what's going to happen to my speed? Speed up or slow down? I'd like to do this so perfectly that right when I come to a stop, that's exactly the same moment that I get to the edge of the universe. I want to be bang on, no wasted fuel whatsoever. That's what we mean by escape velocity. You figured out the exact speed so that when you end up at the edge of the universe, you're also at rest. You've done it perfectly. Got the argument? Really, escape velocity asks, how much kinetic energy is needed to bring your potential energy to zero? Because where is your potential energy zero cosmically? All the way out at infinity. Okay? We can solve for escape velocity by using conservation of energy. So let's write out our conservation of energy equation, which is K E initial plus P E initial equals K E final plus P E final. The final potential energy is out at infinity. How much energy do I have out there exactly as a number? We've defined it that way. So conveniently, and if you want to, you can make a note, because R final equals infinity. We've defined it that way. And what did I say? How fast do we want to be going exactly right when we get out to infinity? Yeah, in fact, I want this to be zero. I want this to be so perfect that I have no wasted energy, which is a little weird, Alex, because what does that mean the whole right-hand side works out to as a number exactly? Okay, I'll commit to it. Mr. Dewick, what does that mean? We don't need any rocket fuel? Patience. What's kinetic energy? That hasn't changed. Kinetic energy equation is? Anyone? Okay, so this is going to be a half mv initial squared plus mgh, or are we going cosmic? Negative big G, big M, running out of room, Mr. Dewick. Little m over R initial, that equals 0. I want to get the V by itself, but I think the first thing, that 0 is creeping me out. The fact that this is negative, Jan, I'm just going to plus this over to this side. And so I'll end up with positive a half m V initial squared equals positive big G, big M, little m over R initial. Oh, will a massive spaceship and a tiny cube satellite have the same escape velocity? Turns out, yeah. Get the V by itself. I guess divide by 1 times by 2. The dividing by 1 isn't going to change anything. So I'll get this. V squared equals 2 big G big M over R initial. Anyone? This is escape velocity. Some kids just memorized it. I am going to ask you an escape velocity question. I'm even going to give you a spoiler. It's going to be an escape velocity from near a black hole, so we get a really big, spectacular answer because we'll be talking about black holes in the next couple of days and how those work. So I'll be even more blatant. You want to know a question on your test? I'm probably going to ask you to find the gravitational field strength near a black hole. Spoiler, it will be way bigger than 9.8. Way larger. Oh, and I'll probably ask you to find the escape velocity from near a black hole. Just for giggles, because I dream of a future where we can do that, I hope. So what's V escape? Usually R initial is the surface of the planet that you're leaving. Or if you're in outer space, how far you are from the center of the planet that you're taking off from. Does anybody remember the equation for orbital speed? Don't write this down, just look up. What was V orb? Well, sorry? It's kind of interesting that will put you in orbit, root 2 faster. What is the square root of 2? As a decimal. 1.41 times faster than that is enough to get you out of the solar system. Okay. This is my concern. Often the kids that memorize this mix it up with this one. I've seen way too many kids when I say find the escape velocity, find the orbital speed, which I'm sorry, I'm giving you a 0 on. So here's the derivation. It's conservation of energy equals 0. Get the V by itself. You can decide which method you want to use. But for what it's worth, let's find the escape velocity for the Earth. It's going to be the square root of 2 big G big M over R initial. What's big G as a number? What's M as a number? Mass of the Earth. What's R? 6.3. You know what? We could write the numbers out, but if you've got them on your green sheet, on your formula sheet, let's go to our calculator. This is one I would encourage all of you to try typing in, though. So I'm going to type in the square root, and then I'm going to go square root answer button. 2 times 6.67. Scientific notation, negative 11 times 5.98. Scientific notation, 24 divided by 6.38. Scientific notation button, 6. I know this answer has to be wrong because I think it's faster than the speed of light. That's not escape velocity. Did you get 11,181? Yeah. I know it's 11,200 roughly. I've just memorized that because I'm a nerd. So, what makes a black hole a black hole? When the escape velocity is bigger than the speed of light. When you solve for V and you get an answer bigger than 3 times 10 to the 8th, that's the definition of a black hole. We'll talk about that in a couple of days. 11,000. That's basically 11.2 kilometers a second. Is that fast? We've done it. It's how we got to the moon. We had to achieve escape velocity and leave Earth's gravity well and get captured by the moon's gravity. We did it. So we've had humans going that fast. We've had probes going considerably faster. The probe that we sent to Pluto a few years ago That was the fastest thing we'd ever sent. There's a joke in NASA. If you're planning on doing a space mission, it has to get there before you die. Otherwise, you're not going to get funding. And so going really slowly to Pluto would have taken about 25 years. No one's funding a 25-year mission because that would be a control room that would have to be staffed the entire time. So they had to come up with a way to get that sucker going crazy fast. So I got to Pluto, I think, in about 8 years. That was the fastest. I need to check. The Parker probe might have gone faster. I think it did. That's the one that's around the sun right now. By the way, it's a really cool one. I think it's hoping to get a sample of the sun. It's hoping to dip into the very, very outer edge of the corona. It's been designed to withstand the heat, and I think it's actually hoping to open up a scoop, get some sun particles, and come up with a way to return them to Earth. It's a very ambitious probe. What's escape velocity on the moon? This one, we're going to write the numbers because I don't know these. So it's going to be the square root of 2 big G, big M. I'm going to put a subscripted little, you know what? I'm going to write moon all over our moon. It's going to be the square root of, I'll write the 2 and the big G. Mass of the moon, it starts with a 7, but I can't remember anything else. Times 10 to the 20. Radius of the moon, I can't remember. What's the radius of the moon? First of all, do you think escape velocity from the moon is going to be bigger or smaller than from the Earth? Just we can make a prediction. We got to get an answer smaller than 11,200. Jan, what'd you get? Sorry? 2,370? This is why NASA is suggesting if we want to colonize the solar system, our best bet would be, Mallory, get a moon base with several thousand people and launch from the moon. So much easier. Because remember, when we're talking about energies, there's that squared in the kinetic energy equation. This is way less rocket fuel required to get to Mars or anywhere else from the moon. Way less. Way easier. Next page. Here's the bad news. That means that meteoroids and asteroids will impact a planet with at least escape velocity of that planet because they're going to gain back all of the kinetic energy while they lose their potential energy and they started out further away from the planet. In other words, when stuff hits the Earth, it's going to be hauling. Of course, it's also possible to reach infinity and still be moving. That work equation, that conservation of energy equation would look like this. KE initial plus PE initial equals KE final. PE final would still be 0 because you're out on infinity. Let's look at black holes. They're pretty cool. One could even say they're attractive. No? Okay. A spaceship is 8.5 times 10 to the 9th meters from the center of a black hole. The black hole has a mass of 50 times that of the sun. Oh, I like this question. I like this question. I like this question. Claudie, what's A asking me to find? You're correct. Say it again, please. Is it saying find the gravitational force? Here is the most common mistake that I see. Kids go, oh, it must, don't write this down. And the problem is, even if you do it right, I have to give you 0. Because it's nice that you found the gravitational force correctly. That would be like if I asked you to find the velocity and you found time. Glad you did. Not what I wanted. What is the gravitational field strength? It's little g. And what is it on your formula sheet? It's that. Right? Really, what I'm saying is actually, instead of you can write that if you want to. I'm saying, look at universal gravitation, the big G, big M1, or M1, M2. Cross out one of the masses. That's what I'm saying. So, Quinn, what is the equation for gravitation? I picked on you already. Sorry. Let's go, Alex. What's the equation for gravitational field strength? Look at your gravitational force equation, the universal one, the one with the big G in it. Cross out one of the masses. So read to me. Don't say FG. We're not finding FG. We're finding little g. Read to me. Big G. Keep going. Don't say little m, because that's the one that's canceled out. Divided by. Thank you. Don't forget the square. That's why I gave you little g in that version. I was to help you see how these are all related. This is the acceleration component of force. All right. Big G. What's the mass? 50 times, what's the mass of the sun? Please make sure all of you know where those are. Divided by, and I guess the radius is 8.5 times 10 to the 9th. Alex, don't forget the what? Okay. Probably going to be bigger than 9.8. Black hole. Alex, what'd you get? I have no idea what the answer is. I'm just quite confident it's going to be bigger than 9.8. In fact, I won't be shocked if it's in the hundreds or maybe even thousands. What'd you get, Alex? Was it 91? Oh, okay, I didn't make it that big. 91.4? Units. Is this a force? How do you know it's not a force? Because what letter am I using here? What is G? You could either say meters per second squared, because last year we treated it like it was an acceleration. But what we can also say is it's newtons per kilogram. We can get the A in F equals what M8 by itself. Either of those units would be acceptable. I usually use newtons per kilogram when I'm talking about a gravitational field strength, because what this is saying is right there, every kilogram is being pulled upon with 91.4 newtons. How fast would a spaceship need to travel in order to escape from the black hole's gravity well? Well, I'm going to rederive the escape velocity equation just for practice. Again, you can decide whether you want to choose to derive it or to memorize it. But deriving it, it started out with conservation of energy. But what did we want our final energy to end up being exactly as a number? Okay. So it ended up like that, and we had a half m v initial squared plus negative big G, big M, little m, all over r initial. We didn't like the 0 or the negative, so we plussed the negative potential energy to the other side. A half little m v initial squared equals positive big G, big M, little m over r initial. They didn't give me the mass of the spacecraft, so I guess I can't. Oh! No, I can still solve this. Why? How would I get the V by itself? Times by, and then square root. Okay, so here's my escape velocity. It's the square root of 2 big G, big M over R. Just make sure you don't accidentally put the mass of the Earth as a habit, because you've done that fairly often. Let's plug in our numbers. It's going to be the square root of 2 50 times 1.98 times 10 to the 30th, right? All over 8.5 times 10 to the 9th. No squared here. I've made a typo. Where's my typo, Mr. Dewick? Did I make a typo? Sorry? 2 times 6.67. Wow. Because I was getting an answer bigger than light. Which, no. At least I was smart enough to notice that, but that was a dumb mistake. Big G, big M over R, square root of that. Dope. Do you get 1, 2, 4? I'll write this in scientific notation. 1.25 times 10 to the 1, 2, 3, 4, 5, 6. Yep. No. Kilometers per second would just be this divided by... I wouldn't mark it wrong. It's just that's not the SI units, right? Yeah. So a little faster than the 11 kilometers per second that gets us out of our solar system. You know what? Let's kick it up a notch. How far away from the black hole is the event horizon? What's meant by the event horizon? That's the moment in space-time. That's the location in space-time where if you go closer, escape velocity is bigger than light. If you're further than that, escape velocity is less than light. Right here is when the escape velocity equals the speed of light. What's this question asking me to find? R. I think if I'm going to be fussier, yeah, this R. I think this is saying find R. You know what? That must mean they told me the escape velocity. What's the escape velocity? It's the speed of light. C. I'm going to take my escape velocity equation, which was V equals the square root of 2 big G big M over R, and I'm going to get the R by itself. First of all, what's the R inside of? Oh, wait a minute. How do I get rid of a square root? Both sides. So this is going to become squared, and I'm going to scribble, 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 scribble. For those of you that like to rewrite things, what I've really just done is I've said V squared equals 2 big G big M over R. Where is the R right now? On the? Yeah. Multiply it to the top. And divide by V squared. Yes? Where is the event horizon? It's going to be 2 big G 50 times 1.98 times 10 to the 30th divided by, who remembers what's the speed of light? It's 3 times 10 to the 8th. Oh, Alex, don't forget the, okay. So let's suppose this is a star that is collapsing underneath the weight of its own gravity. It's a star, it's a star, it's a star. As soon as all of that mass is enclosed in a radius smaller than this, that's when it will no longer be able to emit any light, because light itself can't escape. That's when it turns into what we call a black hole. What'd you get, Keegan? Really? Oh, come on. This is the frontiers of science, my friend. Reed, what'd you get?
147,000.
Can you give it to me in meters, please?
147,000.
147 and then change? Okay. If this star is 148,000 meters large, it's still emitting some type of light. Now, it's no longer what we would classify as a star, because already at that stage, the matter in the center would be so incredibly dense, probably it would already be a neutron star or something special if you dive into the life cycle of stars. But if this star was collapsing and its radius got smaller than that, if you happened to be there and you were staring at where'd it go? I don't see anything there anymore. And the reason is now, to escape its gravity well, you need to travel faster than light, which nothing can do. A stationary rocket blasts off from the Earth and enters into a circular orbit 25,500 kilometers from the center of the planet. Find the work required to put it into a stable orbit. We're not going to do this, but we are going to talk about this, because this is, no pun intended, a lot of work. You're going to try one like this in your homework. First of all, well, Mal, what's it asking us to find? So we would start out by going like this. Okay? Then we would find the change in potential using the cosmic one. Oh, we would have converted this 25,500 into meters. It is a radius, though. It's from the center of the planet, so we wouldn't need to add the radius of the Earth. But we would do, like we did yesterday, negative big G, big M, little m over R, final minus negative. We would use ditto marks. We would enter the first one, maybe the 5 sig figs, write that down, backspace, edit. Okay. Then we would find, this is the one that's a bit different, because what's changing anything? It would be a half m v final squared, technically minus a half m v initial squared, but what did we say v initial was? Where did we say we're launching our rockets from? North Pole? Okay. Did they tell you the orbital speed? Yesterday in your notes, in this question, I gave you the orbital speed. We are in a stable orbit, so we do need the kinetic energy. Now you would have to go like this. Gravity is what's pulling me in a circle. To find the orbital speed, to walk it to there, and then your final answer would be your answer from part 1 and your answer from part 2 added together. That's the extra step from what we did yesterday. I won't do that on a test because it's just, no pun intended, too much work. It's about 15 lines. But, you know, it's got enough nerd coolness. I think I gave you one like that in the homework. Example 5. Xana's going to put her phone away because she's just not that important. You don't need to know this to survive. Example 5. I'm going to show you, Jan, it's called an attention span, a couple of cool patterns that if you have them in your back pocket and you notice this while you're doing a question, oh, I must have got it right. But you will not need to use these 3 patterns to actually solve anything. It's more of a, it's kind of convenient. What does it want me to say? It says, using the expression for orbital speed, which is that, gravity is what's pulling me in a circle. Actually, by the way, what I'm going to do is I'm going to write v squared equals big G, big M over R. I'm going to get rid of the square root. You'll see why in a second. Sarah, what's the first thing it wants me to prove? Read part I. Stop. Say that again. Okay, KE, a half mv squared. What do we want me to show? It's half the magnitude of the... By the way, let's write over here on the left. PE is negative big G, big M, little m over R. It wants me to show that this in orbit is this divided by 2. Let's see. What is V orbit? Well, V orbit is this. What's V squared in orbit, Sarah? Read those 3 letters to me. I'm going to replace that. I'll leave the 1/2. I'll leave the M. I'll replace it with big G, big M over R. And if I tidy this up, Sarah, is there a big G? Say yes. Is there a big M? Say yes. Is there a little m? Say yes. Is there an R? Say yes. But in the front, there's that. Can you read to me point I again? What did it want us to prove? Kinetic energy is what? Half of the potential energy, but magnitude, but positive. Yeah, you know what? There's potential energy, except potential energy is negative. Turns out kinetic energy is half as big. If you happen to notice, and I'll make up some numbers, that your potential energy is negative 12 times 10 to the 10th, and you happen to find that your kinetic energy is positive 6 times 10 to the 10th, you've done it right. That can't be a coincidence. But that's why I said it's a handy little error check. It's not something you need. Sienna, what does the second thing want me to prove? Total energy. Well, total energy would be the potential plus the kinetic at that location. I think that's what total means. The potential energy is negative big G, big M, little m over R. And we just showed the kinetic energy is a half big G, big M, little m over R. Sienna, aren't those like terms? They are. They each have a G, a big M, a little m, and an R. What number is in front right here? It's invisible. We never bother writing it, but this is technically negative 1 plus a half of the same. What is negative 1 plus a half? Negative a half. Big G, big M, little m over R. Can you read to me statement 2? Total energy is what? Yeah, it is. If you notice that, you've done the question right. Lena, what's the third pattern? Stop, that's that. Keep reading. Are those two numbers the same, but one's negative and one's positive? Yeah, we kind of proved it along the way. Again, let me emphasize, you don't need to memorize this. It's just kind of a neat little pattern. I've used it once or twice when I've been doing a complicated calculation. Oh, look at that. It is the same. Or it is a half. Good, I did this right. This class ends, I think, at 10:45. Okay, so patience. What I'd like to do is look at all the various ways I can give you launching a rocket and what I can ask. So example A says this. A rocket at rest, I would probably underline the word at rest, on a surface blats off from rest, especially since they said it twice, and rises to a maximum altitude or height to a maximum distance, big R, like the picture. See the difference between the height and the radius? Write equations to calculate the work done by the engine. Okay. Emilio, what equations does this want me to write to calculate what? Force times distance? What?
Changing.
In fact, it's going to end up being negative big G, big M, little m over big R, that seems to be R final, minus negative big G, big M, little m over little r. Would this object, would this rocket stay in space once we shut the engines off? Why won't it? Why will it come crashing back down to the Earth? What do we need to do to put it into a stable orbit? Not just give it potential energy, but give it what kind of energy? We would have to then turn it sideways and fire the jets for a while. So this is how much work required to lift something up into space. This will not keep it in a stable orbit. Why? Because the orb is 0. That won't get you there. Right, Alex? Okay. A rocket moving at speed v at liftoff near the Earth's surface rises to height h with no engine use. I guess we fired our rocket in one mighty burst and then we coasted the rest of the way. Write an equation to calculate the maximum height using conservation of energy. Assume the rocket ends at rest. Did this question ask how much work? No? Okay. So what am I going to use here? If I expand these, it ends at rest, so I can say, ha-ha! The question told me that. But it also specifically said it doesn't start at rest. Here's what as far as I'm concerned, change colors, Mr. Duke. This is what I can ask. If I go a half m v initial squared plus negative big G, big M, little m over r initial equals negative big G, big M, little m over r final. Could you use this to figure out the mass of the rocket? Why not? Okay. I would have, as far as I'm concerned, I see 3 variables here. V initial, R initial, and R final. If I give you any 2, you can find the third. I would not try and get the V or the R by itself. I would get their expression to one side. I would put everything else on the other side, crunch it, turn it into a number. Only then would I try and get the V or the R by itself. I wouldn't try and do this one algebraically. In other words, if we know how much kinetic energy we start with, we can calculate the final radius and figure out the height. A rocket moving at speed v at liftoff near the Earth's surface barely escapes Earth's gravity with no additional engine use. Write a conservation of energy equation that would... what do we call this? Well, this is escape velocity. It should be called escape speed because it's a scalar. But okay. What was our equation here? Kinetic initial plus potential initial equals kinetic final plus potential final, except what was our final potential energy for escape velocity? And what was our final kinetic energy? And then you can rewrite this and get the V by itself. We've done that a couple of times in today's lesson. I'm not going to repeat it. You can go look. What else can I do? Yeah, turn the page. Wolf, what's D you want me to find? Okay. Look at the picture. Are we in a stable orbit? Did the question say we're in a stable orbit? Then here, the work is going to be the change in potential and the change in kinetic, where we're going to find the change in potential separately, put a box around it when we're done, then we'll find the change in kinetic. We will still assume we're launching from the North Pole. That's why it says assume the rocket starts at rest. Okay? That's fair game. I will give you the orbital speed when I ask you this question. I won't make you calculate it, but in your homework, there will be one today just for giggles where you have to calculate it. No pun intended, this question is a lot of work, a lot of writing. Ooh. Okay. Francesco, what's E asking us to find? How fast? Are we in a stable orbit in E? Not if we're crashing into the Earth, we're not. No! That's the very definition of not a stable orbit. Whoever said yes. We're crashing into the Earth. So don't be telling me gravity is what's pulling me in a circle. Also, you don't see the word orbit anywhere in this question. Is this question asking how much work? Then how will I solve this? Conservation of energy. G. K E initial plus P E initial equals K E final plus P E final. It'll end up being a half M V initial squared plus negative big G big M little m over R initial equals a half M V final squared plus negative big G big M little m over R final. The little m's will cancel. As far as I'm concerned, this question, which is a little tougher, has 4 variables. Initial speed, initial how far you're starting from the planet. By the way, you're starting in space, your initial will be what's usually the final, will be the initial. You're starting in space, it'll be the bigger radius. Your impact speed, V final, or how far you've fallen if I tell you how fast you're traveling at a given moment. If I give you any 3 of these, you can find the 4th. And again, for all of these, I would not get the V or the R or the V or the R by itself. I would get everything else to the other side, turn it into one number, crunch it into a number, then I would get the thing by itself.